We have tens of thousands of different environments that we've built, and we're always building more. The more environments we're able to build, the better we're able to push our teacher models forward. The types of environments we're trying to build are diverse, since we're trying to make an AI that can solve diverse kinds of tasks.
I'm very excited to have Bryan here to talk to today from Nvidia. And today we really want to dig into what it takes to build a large language model these days. And what I want to start with is Nvidia has been really on a roll with building up and releasing more and more interesting and smaller models, larger models. And I really want to understand, what does it take? Like, how come you kind of went from maybe releases once every 6 months, once every 8 months, and now it feels like we're seeing releases every maybe 4 to 6 weeks, and we've seen like a couple of releases from Nvidia very quickly. So how come we see that change?
I think there's two things that are coming together to make Nvidia's investments in AI technology a little bit more visible. The first is just, I think, an increasing sense of understanding and unity around the company about how important this work is. In the past, AI was a science project. It was research that, researchers like to do in a lab. And as AI has developed and become more and more broadly deployed, it's become obvious in more ways to more people around NVIDIA how core this technology is to our future. That has then inspired a lot more participation and a lot more building of the team and the sort of the sense of mission that we have in NVIDIA about what we're building, which I think is directly connected to the quality and the amount of the work that we're able to do. The second thing has to do with infrastructure. So, NVIDIA is an infrastructure company. We help the world build infrastructure for AI. And yet it's taken us some time to invest in our own infrastructure, which we are doing in a much more serious way these days. And so it is absolutely true that the more GPUs that we can bring to bear to our AI research, the stronger and larger that research gets.
That's interesting. I think it sounds like, and I do pick this up from the various teams, it sounds like once a team gets momentum, it seems like one model after another. But obviously infrastructure, what you see coming out of NVIDIA, it sounds like, the infrastructure side is really top notch. What do you think in terms of things like data and algorithms and kind of what you also get from the kind of maybe open source community? How much do you think pushes the progress forward for you?
I mean, that is all critical. We work really hard on all of those directions. Maybe we should start with the open source community. NVIDIA loves the open source AI community. We love reading papers that other people put out with really great ideas. We love using data sets that have been posted on the internet that illustrate ways of solving problems with data or new approaches to solving problems with better data. We love models. We love open source models. We use them extensively. If you read our tech reports for our most recent Nemotron models, we list, all of the different open source models that we use for synthetic data generation in order to build up the data sets that we create Nemotron with. And it's quite extensive. We use all sorts of models from all over the place. And many models have their strengths, right, in different ways. We're very grateful for all of that contribution that's coming from the open community for AI, and of course we want to contribute back to that because we know that it's directly connected to our business. The more companies that are building and deploying AI, the more opportunity there is for NVIDIA. We know that open technologies for AI are a critical part of that, whether that's data or ideas or models themselves. We benefit greatly from the community, and we also try to contribute back as well. It's in NVIDIA's interest to keep that open community strong and robust.
Definitely see that from NVIDIA and that kind of support. I think one kind of direction I want to test as well is, if we imagine we went back, I don't know, a couple of years or maybe 3 years, and we said, okay, the processes, the data algorithms, techniques, all the same, but we have hardware that is different. So if you're magically given like a GB300 or what's the kind of your hardware of choice, like how much difference do you think the hardware part would make here?
These things build on each other. It's difficult to separate because when we increase our computational capabilities, that allows us to explore more ideas. Figuring out which ideas we can explore without having the chance to try things out is actually quite challenging. One way to think about this, if I look at our compute allocation for Nemotron right now, I would say probably 30% of our compute allocation is running synthetic data generation from our own models, from other models that are out there in the community. Why are we doing that? Well, because it's actually a really important way of improving our core AI technology, is to basically use language models to create synthetic data that helps strengthen areas of our intelligence that we know need to be strengthened. Now, if we turn that down, right? So if we say, well, using the hardware from a few years ago, that just means it's a lot smaller. So we just have a lot less capability, a lot less capacity for synthetic data generation. How does that change the way that we build our models? I mean, they're not going to be as smart. It is definitely the case that the vast majority of compute that goes into building an LLM these days is not training the actual model. It's in developing the data sets and the techniques that we use to train the model. If we reduce the amount of capacity that we have to do that technology development, I think ultimately it just means that the underlying AI is not going to be as good. And you can kind of see that. I mean, it's never been like fully discussed, I believe, but I think GPT-3 was somewhere around 100 billion parameter model, right? Somewhere approximately 100 billion parameter
175?
model. Compare that, for example, to Muse Glimmer, which is a 30 billion parameter model. So it's like, wow, Muse Glimmer is like way smaller. It takes way less compute if you just think about the number of parameters, right? But then Muse Glimmer is trained on vastly more data, vastly higher quality data. It's post-trained with new techniques that didn't exist back in the GPT time frame, and the capabilities of a model like Muse Glimmer compared with GPT-3, I mean, it's just apples and oranges, right? Like the field has moved really, really far. It's not the raw compute that goes into the model that made all that happen. A lot of it was work on data, work on techniques, and then basically increased understanding of how we go about building these models, which comes from experience, which also is related to how much compute we have. The more compute we have, the more experience we gain. It's difficult to separate those things out. Another thing to consider is like, if you already know what to do, it's much easier to repeat it. If I'm allowed to have all the data sets that I have and know all the things that I know now based on the compute that we've put into inventing that over the past few years, if I'm allowed to keep all that knowledge and all that data and then go back and have the compute of 3 years ago, what could I do? I could still do something pretty good. But it took an enormous amount of compute for us to get to there.
It's actually interesting you mentioned about the synthetic data generation. I've never heard this stat about 30%. I do remember hearing about these ideas. It's like, oh, now we are spending all of our compute like training the model, but actually then we'll be trading kind of compute further up the kind of the training stack. How do you think about the compute allocation? Do you even think about it model by model, or is this kind of one big process right now?
Oh yeah, we have a very careful process about that. So every lab is different, and I don't believe that our way of doing compute allocation is the best way necessarily, or the only way for sure. But we have a roadmap. We have a way for people to contribute ideas. Like there's tons of ideas that go into building an AI, and along with those ideas comes compute, right? Because it takes compute to evaluate those ideas and to integrate them together. And so we have that all modeled in a system that we use that helps us decide how we're going to direct our compute in order to build the core technology that goes into our AI. And then, of course, when it comes time to actually build a model that we're planning to release, then the compute for that is also very carefully modeled and allocated. We usually run for our big runs, like let's say for Nemotron Super or Ultra run, we typically will run on a reservation where the cluster is basically locked down and just devoted fully to pre-training or post-training that particular model. Everybody else in the project is excited about that. They're like, Of course, I will slow down some of my other work. I will do anything I can to make sure that the model you're building succeeds. And so that all has to be planned out and scheduled.
Actually, how do you think about this kind of the larger training runs versus the smaller runs? Because the kind of intuition, and I had this in kind of guess almost, but I want to test with you as well, is that like when you do big runs, it takes longer for you. Obviously, it takes longer to train, more compute. Maybe you can't do RL as much on it versus like smaller models. You can like keep going with RL. So like, do you kind of take a portfolio view, or how do you think about the kind of the big versus small?
I think the best way to develop this technology is that we iterate quickly and push along our core data sets, our techniques, our algorithms, figure out how we're going to use these RL environments, how we're going to integrate them all together. We do that at, I wouldn't say a small scale, but a medium small scale. When it comes time to do, Nemotron Ultra, then, we're just going to push the button and we're going to watch it, of course, really carefully. But it's not possible to do all of the experimentation at the large scale. We're always going to be running at the limit. So the research needs to happen at small scale, pushes the technology forward, make sure that our data is as clean and as intelligent as we can get it. And then we apply it to the big model, and it, hopefully does amazing. And meanwhile, we keep pushing the core technology forward. And that should be independent of actually building the big model. At Nvidia, since a lot of Nvidia builds chips, we often call it taping out a model. In the same way that we tape out chips, we tape out models. But the tape out process, that happens kind of independently of the core underlying progress in the technology that's pushing the intelligence forward.
It's actually interesting what you said about the kind of the smaller models where you do the experiments and then you do the big model run. Because I think the intuition, what I hear a lot from people is that, the labs have the big models and then they kind of distill them down into the smaller ones. Which way around does it go normally? Or is it kind of both?
It's like, which came first, the chicken or the egg, right? It's like, well, you kind of need both. They all influence each other, right? So a really excellent big model, we're going to use that as best we can to make excellent small models. And then we're going to experiment on the small models, increase our technology, use that to make a much better big teacher model. And, it's a bootstrapping process. Like anything else in technology, you can't start at the end. You have to start at the beginning, go step by step. And so there's a little bit of an alternation, I think, that happens. And this is based on, our judgment on the ROI of the different ways of spending compute, right? Like, of course, like in everybody's ideal world, everybody would love to do all of their research with ultra-sized models. But again, that's not feasible. It's not a GPU supply problem, because if we had, let's say, 10x more GPUs, we would just make the ultra model 10x bigger, and then we'd be exactly at the same place, right? So since we're running at the limit, I think this is a fairly fundamental thing. And it makes sense to me also that like research that shows promise at the small scale, it's necessary for that to happen in order to see progress at the big scale. What I'm saying is not 100% true. There are some phenomena that emerge with larger models that you don't see on smaller models. And so, we have to be mindful about that. We typically deal with that through scaling ladders where we de-risk things. So we have this collection of ideas that we've shown have some benefit at smaller scale, and then we integrate a bunch of them and try them out at a medium scale and see how that goes. And so there's kind of a step-by-step process by which we take ideas from the small scale to the big scale. But, ultimately, I feel like this question of how do we do research that pushes our technology forward versus how do we tape out, the biggest model that we can possibly tape out, those things imply that we will always have to be kind of cycling back and forth. We can't just do everything at the small scale, and we can't do everything at the big scale. We have to be smart and use them all, but at the right time.
That makes a lot of sense. And I think one thing you mentioned is the teacher model. And one thing I'm curious about is you kind of, I don't know, hear the kind of gestures towards this. I don't know if there are rumors or people just guessing or kind of maybe wishful thinking that labs have these massive models that they use as teacher models. Like, do you think there's any merit in this kind of structure? Or is it like when you train a big model, actually, no, you do want to release it because it's otherwise impractical?
I have no information about what's happening behind closed doors at any other institution, so I don't want to speculate about what other people are doing. But what I can tell you that we do is that we use this multi-domain on-policy distillation with a whole bunch of teachers to push Nemotron forward. And we do this for two reasons. One is a technical reason. AI is fundamentally an integration problem because AI needs to do all of it, right? It needs to be good at coding. It needs to be good at science reasoning. It needs to be good at writing poetry. It needs to be, whatever. If you look at the breadth of tasks that we ask our AI to do, it's quite large. If we didn't have a way to push each of these things forward and kind of get a sense of how good can we get without constraints, without having to worry about the integration for the whole larger project, we would probably not be able to push the technology forward very fast because pushing the entire frontier forward across 100 different types of work is much harder than just pushing in a single direction, right? And so we want to know, like, how far can we take a particular domain? And then, so that's a technical question of, we just want to develop the technology, and it's best to do that with independence, right? So we can orthogonalize, decouple things. But then there's also the managerial aspect and sort of the difficult integration problem where it's like, okay, imagine we have like 100 teacher models. They're all amazing. And now we have to put them into one model. How do we do that in a way that, is fair, right? And we would prefer, of course, to make a non-zero sum trade-offs, right? We don't want it to become a whack-a-mole problem where like we make it good at one thing and then it's bad at 99 other things, and then we make it a little better at 99 things and it's bad at, so we want to avoid that. And so we found that this MOPD technique, we've been using it for a long time, that it provides both of these capabilities, that both the capability for us to move our technology forward, as well as an organizational capability that we can have many, many teams, each working on their own area and pushing their own area forward with confidence that the progress that they make will ultimately be integrated into one single model that we can release. So that's been, I think, a really important part of building our AI. I always like to think about the impact of AI on the people that build AI. It can be pretty large, right? Having a technology that allows the people building the AI to feel empowered and to feel like they're not in competition with the other people they're working alongside with, to feel like we're really doing an integration project where there's going to be lots of teams building lots of things. It's all going to come together into something amazing. That's a really important feeling to have when you're trying to build a team, a large team that's going to build an amazing AI. And so this technology of using teacher models and multi-domain on-policy distillation has been really key for us in these ways. Now, what does that mean? Well, it definitely means that inside NVIDIA, we have a collection of teacher models that are individually better at different domains than any of the models that we've released. And actually, I'm trying to release those teacher models as part of the Nemotron project as well. Because as you know, Nemotron is not just a model. Nemotron is an open technology effort. It includes data sets. It includes techniques, all of our ideas about how to build a model, which we publish. Of course, it includes the models themselves, but I think it should also include collections of teacher models. I'd imagine this could be a really great way of federating open technologies for AI across the ecosystem. Let's say we put out our coding teacher model, and there's some researchers somewhere else, maybe at another company or maybe at a university, that they can focus on just making the coding teacher better at something, right? And then they put out a better coding teacher, and see the nice thing about that is that like we can then work together without having to be in each other's way. That's kind of the dream that I'd like to get to. So although we haven't been releasing our suite of teacher models, I hope to do that. And I hope that by doing that, we'll spur innovation around the ecosystem.
I love this idea because I've never thought about it this way, but I think it is kind of odd how certain capabilities you just have to wait for the different labs to prioritize, and like all of the models were really bad at Excel. And now they certainly got better just because probably they prioritized it. But I guess for model your suggestion, maybe few people who really cared about it could have like built their teaching model and then contribute that back. So
Right.
that kind of structure makes sense. One thing I'm curious about. So when you do kind of have these teaching models, I assume that kind of comes from these reinforcement learning environments that you mentioned as well. I actually don't have like a very good idea of like what is a very good reinforcement learning environment. Could you share a bit more about that?
It's complicated and they're quite diverse. I mean, we have tens of thousands of different environments that we've built, and we're always building more. You know, I think we should have like hundreds of thousands of these environments. We definitely know that the more environments we're able to build, the better we're able to push our teacher models forward. It definitely is directly connected to the strength of our teacher models. But they can be quite diverse because the types of environments we're trying to build are diverse, since we're trying to make an AI that can solve diverse kinds of tasks. It's a little bit difficult to describe them, and I don't actually know the details of all of them. I just know that we have a large effort building them, and we're trying to make it much more diverse and bigger.
I guess if you do, if imagine, hundreds of thousands, I imagine it's probably going to be like extreme level of detail where you kind of have to like create each one for different tasks. Like, do you see that kind of structure? Do you see that as it kind of a model that also applies to kind of less verifiable tasks? I don't know, writing poetry or something like that. Like, do you see that working as well?
It's harder with tasks that have softer verification. It's obviously harder to build good environments for them. But I think there's no question that a lot of the domains that AI is most useful for don't have the same kind of verification as, let's say, coding does. And so it's important for us to be able to build environments. It's interesting, like, we often use LLMs as judges as well. Even for these environments that have kind of softer rewards, we can use LLMs to be the judge. And of course, they're not going to be perfect, but I do think generally that it is an easier task to analyze something and judge it and give it a score than it is to come up with the solution. And so it's maybe okay to have a weaker LLM than the one you're building be the judge. It's going to have some sort of signal that's going to help provide some sort of guidance about, like, is this poem written well, for example. Even if it might not be as good at writing a poem, right? And of course, poems are not the most important thing, but I'm just using that as an example of something where the reward might be a little softer. We do a lot of that. And, that also is interesting as a systems problem because, when we think about how much compute we're devoting to reinforcement learning, a lot of it is then going into inference in different ways, right? Inference from the reward model, obviously inference from the rollouts, and then sometimes inference in the environments themselves. I feel like the role of inference in building AI has been not discussed enough. We understand what training is, but in an environment where the model's trying to learn and then be judged, the systems problem becomes much more about inference than it used to be.
What do you see as a trend in terms of like training versus kind of inference during training? I'm guessing before it used to be like 100 to 0. What do you see kind of is going towards?
I mean, during reinforcement learning, during post-training, it's probably somewhere around 50-50 right now.
Oh, wow.
And then, of course, pre-training is still 100-0, but post-training is probably more 50-50. But I think it's trending towards more inference than training during post-training. Our systems effort is taking inference much more seriously for post-training than it has in the past. We're trying to make that much more efficient. We're trying to make it so that different jobs can be batching better and, dealing with bubbles where, if you have an AI that's doing something complex in an environment that doesn't need inference, like, for example, compiling the Linux kernel or something, right, where it might take a minute or something to go off and do that. You would prefer not to hold on to a bunch of GPUs that are waiting to do inference and judge the output or, update the weights. You'd prefer to not hold those GPUs while that's doing its thing. And so how can we decouple these things better? How can we get better utilization during post-training? Really, really important systems problem, really interesting problem for NVIDIA. as we're thinking about what kind of infrastructure to build, we know that infrastructure for post-training is going to need a lot more CPUs. We're really excited about the Vera CPU that we recently released. We think it's really excellent for agentic workloads and especially for post-training. I think over time, these environments are going to become GPU accelerated as well. It makes sense to me that these environments are going to have simulation of the real world, physics simulation and so forth. Those are GPU accelerated environments. So if we can, make it possible for AI to learn how to interact with the real world faster because it's simulating things in a GPU environment. That's obviously a very interesting problem for NVIDIA to work on.
Definitely, when I start running my agents, so much of the time it's just CPU time, they're doing non-AI work. I definitely see that kind of in day-to-day use. One interesting thing you mentioned about LLM-as-a-judge is maybe the model doesn't need to be as smart and maybe it could be smaller. It's interesting because for humans, it's not how it works, right? Normally, it's the more senior person is reviewing the work and judging the work. Do you think, is it actually not a good analogy with humans? Is it like some other artifact of human relationship that it worked out that way? Or is it just kind of more practical consideration that you don't want to run very big models as judges?
It's true that our education system, we have teachers and students, right? And the teachers provide the grades, but students often provide grades too. And if you are given the task to decide, is this poem written in the right meter, and does it have the right rhyming system, and does it express a particular meaning? It's much easier to read through a poem and assess those qualities of the poem than it is to write the poem, right? It is not symmetric. If you're given the brief, you're given the assignment, write a poem with these characteristics. That's much harder than, does this poem conform to these characteristics, right? It's just an inherently easier task. That's my experience anyway, is that it is possible to use last generation's model as a judge to create next generation's model. And the next generation model becomes meaningfully stronger because last gen model is actually pretty good. It's good enough that it can give signal even for tasks where the rewards aren't as easy to verify. We can still rely on last gen model to give us some reward.
That's interesting because I think I have heard other opinions from others in terms of saying, oh, you must have access to, I don't know, Fable so it can judge your work. But that's interesting. Maybe you don't need to. Maybe you can actually use the.
Yeah, that's not how we work. We definitely don't work that way. We've definitely been able to push our AI forward using last gen models as the judge. We are still able to push the model forward that way. Now, would the model push forward faster if we used a better judge? Well, that's an interesting question, which I think relates to compute constraints. So obviously we don't use Fable as part of our judge because I think I'm not even actually sure if that is allowed under the terms of service. I'm not a lawyer, right? But in NVIDIA, we don't develop Nemotron with Fable in the loop. No, we don't do that. For the models that we do have, access to that we're using, it's definitely a compute allocation concern, right? We're thinking about what's the ROI. So we typically we're pretty pragmatic about this. So we try some things, we see what we can afford, we do the best thing that we can afford. And we know that tomorrow the model will get better and we'll have more GPUs too, hopefully. And so for the next round, it'll be smarter and bigger. But, for this round, we'll do what we can. And, it's the bootstrapping process of building AI.
On the topic of judges, I want to ask you about evals a bit more. So it sounds like maybe when you kind of need to use LLM as a judge, and I imagine it's kind of environment specific. But how do you think about evals? Do you run all of the benchmarks that we know about, or is it kind of a mixture of the different ones?
Evals are really complex. And by the way, we love Arena. We've been working with Arena a long time. We're very grateful for the evals that Arena oversees, which are in a lot of ways gold standard, right? I think Arena pioneered gold standard evaluations and continues to push those forward, and we're very grateful for that. Definitely helps us make our models better. But inside Nemotron, there's quite a few different ways of thinking about evals. We have a centralized evaluations team that keeps our methodology centralized. Evaluations are very complex, especially these days with agentic workloads. They can take a long time, and there's a lot of ways to take the same model and get wildly different numbers from the same task, depending on what harness you used or like what settings you used. We have a centralized team that does that. We also have researchers that spend a lot of time working on that. So for example, it's often the case that there'll be an excellent open model that's released and it'll claim a score on a benchmark that we love and care about. And so we'll try to reproduce that. And that can take some research actually to figure out the right combination of harness and setting and so forth that allows us to use the model in the way that was published when that model was released. That research I feel like has been really important to our own work, because like figuring out like how to talk to a model to get it to solve to a problem, even if it's a different model that's different from the one we're building, kind of helps us understand the space better, which then helps us build our own model better and evaluate it better. Of course, with Nemotron, we're trying to be very open. So we're trying to publish all of our evaluations. So when we say Nemotron gets 73 on some evaluation, we want to be able to point you to the script that we use to get that so that you can easily reproduce that and then hopefully make it better. Nemotron is a unique AI effort in the sense that we're not trying to be the only one, and we're not trying to control the way that AI is built or deployed. What we're trying to do is support. We are happy when other people do great things. When Muse Glimmer came out, we were so happy about that. That's amazing. This week, we've had so much great news. DeepSeek has put out a great model. We're happy to see Grok doing amazing things. Of course, Anthropic and OpenAI, they just keep chugging along, doing amazing work. That is all opportunity for NVIDIA. So we're not engaged in a zero-sum endeavor with Nemotron because our goal is to grow AI. We know that when AI grows, NVIDIA's opportunities grow. So we don't need to worry about some of these things in the same way that maybe some other efforts do. And that's why we can be very open about what we're doing.
Brilliant. I think this is a great place to end. I've been super impressed with NVIDIA's openness, and really your quality of answers today really showed the openness as well. I really appreciate your insights and the depth you went into. So thanks a lot.
You're welcome, and thanks for having me. Thanks to Arena for doing great work to help the ecosystem develop and move along. And I can't wait to see what we as a community, as an ecosystem, can build together moving forward.